Okay, so good morning, everybody. Thank you to be here. So, of course, I would like to thank the organizers for this wonderful conference. And, of course, I should dedicate this talk and even this conference to a person. Okay, this picture was drawn by Andrei Nachmin, and he had written something there that I tried to translate. It makes more sense maybe in Portuguese, but of course. But the idea is that really Jacob Palace was an idea. Certainly without whom and other singular people like him, like Abdus Salam and others, we could not be here. Okay, so let me go through the talk, which is the continuation, the continuation of the course that Jérôme Bouzy began yesterday. And fortunately, he arrived to talk to us about the variational principle. So Jérôme defined for us, okay, I could not lose this blackboard, defined for us the variational principle and defined a notion of topological entropy along the foliations. So whenever I write HU top, I mean unstable topological entropy. And let me assume that everything today is a partially hyperbolic diffeomorphism. Instead, when I explicitly say about that, and HU is the topological entropy along the unstable foliation, and it is given by the supremum of the entropy of the measures which are invariant for the dynamics. And as Jérôme said, we always have a partial hyperbolic diffeomorphism, always has a measure of maximal U entropy. So UMME today will stand for a measure of maximal entropy. So the measure of the U entropy of this measure is equal to HU top of the diffeomorphism. Okay? So we always have these measures of maximal entropy. So one of the first questions when you begin to study unstable entropy is the motivation. Okay, so why do we care about unstable entropy? Like many other things in dynamics, it serves as a technical tool, but also can be useful to developing some new topics and theories too. So let me begin with the first result that shows one of the importance of this entropy. And this is a recent result by Maria José Pacifico and Juan Carlos Monges. So they proved that, okay, you know, we defined unstable entropy in the same way. You can define a stable entropy, which is just the unstable entropy of the inverse of the dynamics. So stable entropy is the unstable entropy of the inverse dynamics. And there is not necessarily a symmetry, of course, between these two entropies. And in the recent paper, they exploit the asymmetry of between unstable and stable entropy. So if you consider a partial hyperbolic diffeomorphism, which is C1 plus alpha, and the unstable entropy is larger than a stable entropy, then robustly, I mean, all of the perturbation has finitely many measures of maximal entropy. This is measures of maximal entropy, not a U measure of maximal entropy. So this is going from unstable, some partial thing, to something on the global measure. Yeah.
So does the
Yeah. Yes. robust. Yes, they will be robust. So let me just very quickly say about the proof. So the proof goes through, first, the main idea is that high entropy measures are very well hyperbolic. And then after some additional arguments, you prove finiteness or uniqueness if you have more minimality of your dynamics. For instance, if unstable and stable foliations are minimal, you can get more. And maybe the main thing is that if you have this asymmetry, then all large entropy measures should be hyperbolic. So if you take any measure, mu, such that its entropy is larger than the stable entropy of F, okay, so large as this, as large as Hs of F, then what do you conclude? Okay, we should use the result that Jérôme stated yesterday. So we know that, first of all, the center-Lyapunov exponents of this measure cannot be positive. It should be negative. So why it should be negative? It should be negative because if it were positive, then, okay, why it should be negative? The center exponents of it should be negative. Why it should be negative? Entropy of mu and F is equal to entropy of mu and F minus 1. And this will be, okay, if the exponents are positive, then the exponent of the F inverse are negative. So the exponent, if not, the exponents of F inverse are negative. And as soon as these exponents are negative, you can conclude by this entropy formula that the entropy of mu of F minus 1 is less than U entropy of F minus 1, which is exactly S entropy of F, which is a contradiction as you assume the entropy is larger than Hs of F. So it should be negative, but you can also, in fact, you can prove that it should be as negative as what I wrote. In fact, prove that lambda C of mu is less than the gap between lambda S and F and lambda of F. So again, use the same thing, the same kind of proof. So you say that, okay, if I take F inverse, what do I have? I know that what? The entropy of F and F inverse is less than, so you have Ruel-Margulis formula, less than the entropy, unstable entropy of F inverse, which is a stable entropy of F, plus the exponent of F inverse, and the exponent of F inverse is minus lambda C, the minus of exponent for F. So here you conclude that lambda C should be less than Hs of F minus H of F. Okay, yeah. Where? Here? Before? So lambda C of mu, H. Yes, this is not lambda S, this is Hs of F. No, this is Hs of F minus H of F. Yeah, thank you. So as soon as you prove this gap, this means that high entropy measures are sufficiently hyperbolic, and then you have these technologies using ergodic homoclinic classes defined for the measures, adapted for measures of maximal entropy, and then you use police kind of lemmas to prove that the ergodic classes are large, and then you prove finiteness. So, okay. In general, it is interesting to understand what is the relation between the unstable topological entropy and the stable topological entropy. Of course, if you consider very, very stupid examples of higher dimension, you can cook up examples that the unstable entropy and the stable entropy are too different. You consider some Anosov with many bundles of unstable, many bundles of stable. But what is more, maybe the setting that is more interesting to play with this game is the one-dimensional center case. So let me be in the one-dimensional center case. It is a relatively old result of Vaughan and Thomson, Kliman-Haga and Thomson, that they proved that if the supremum of entropy along measures with positively Lyapunov exponents is different from the supremum over negative exponents, then you have unique MME under the condition of minimality of unstable and stable foliation. And in fact, this condition of Zeze and Monges, they imply this condition. So if HU is larger than HS, then the supremum over the entropy of measures with negative exponents will be strictly larger than supremum of the entropy of measure with negative exponents. So this result is kind of corollary. And in fact, they don't assume even minimality of the foliations. So you don't need minimality. Okay, the technologies had developed, and we have much more things to prove. So in one-dimensional center, so this is not very good to use both Blackboard and in one-dimensional center partial hyperbolic diffeomorphisms, what happens if you have the symmetry? If the topological entropy, U topological entropy is equal to S topological entropy. So in this case, if HU top is equal to HS top, then what happens is that, in fact, it is the full entropy. Then it is the full entropy. Full entropy equal to HU top. Okay, and the argument is, again, using this kind of formula. Okay, I should first say the result. Okay, what we use to prove these results is a Ledrapier-Young formula where we use C1 plus alpha regularity. So how do you prove that if HU is equal to HS, then HU is equal to HS equal to H top? So suppose that it is not equal. So you have measures of higher entropy. So if you have measures, so if you have HU equal HS and your H top is here, so you have measures of entropy larger than HU equal to HS, and then what you can say is that, okay, the entropy of this measure, mu, the full entropy of this measure is less than, in fact here I don't use the full Ledrapier-Young. Entropy of the measure is less than the U entropy of the measure, okay, plus some of the positive Lyapunov exponents. Okay, if it has positive exponent, you change to the negative exponent, so you can assume that it has negative Lyapunov exponent, so it is always less than the entropy, which is less than the U top of F. Okay? This means that you cannot have any measure of larger entropy. So here I think that we don't even need the C1 plus alpha as we talked. Okay, I will use the C1 result that I announced here later. Okay? So there are at least two important settings where these HU and HS are equal in the one-dimensional center case. In the one-dimensional center case, there are at least two settings of partial hyperbolic diffeomorphisms. Maybe tomorrow will appear a bit more, these two settings. One of them is the fibered partial hyperbolic with one dimension. You can consider, if you want, a skew product. So here I mean partial hyperbolic diffeomorphism with circle center leaves. okay? So, and another setting where HU equal to HS holds is the so-called discretized annus of flow that I hope that I can go through tomorrow, annus of flow, which are kind of new, nowadays not too new, class of partial hyperbolic diffeomorphism. I'm sorry, the citation to Diaz, Gelfert, and Ramsey is not correct here. It will appear again later. So in these cases, what do I mean in these cases? I mean in these cases where HU is equal HS. So in the cases that dimension of the center bundle is equal to 1 for F partially hyperbolic, and dimension of EC equal to 1, and assume that HU top is equal to HS top, then as I said, it is equal to H top, then you can conclude that the union of U measure of maximal entropy with S measure of maximal entropy is exactly equal to the set of measure of maximal entropies. So, okay, if you want to understand measures of maximal entropy, you should look for this union. And this union can be the same, can have intersection, and it will happen that there are some points that belong to one of these sets and does not belong to another set. And this will be the application of my talk tomorrow, which is our plan of talking about invariance principle, where we go through to understand really being U measure of maximal entropy, how much differs from S maximal entropy, so in terms of who knows invariance principle. Okay, so this is the corollary of this. One of the first corollaries that I would like to tell you about the importance of measures of U entropies. Okay, so right now I have a question, we have a question, okay, and the question is that consider an Anosov diffeomorphism on 3 torus. Suppose that you have this decomposition, so you have a strong bundle and weak bundle, which is unstable, then is it true that the U measure of maximal entropy is measure of maximal entropy? Okay, this is kind of rigidity result that people are working for some years. I have written it in a survey. I would like to thank Lorenzo Gias for encouraging me to write this survey about U entropy. And at the same time, this appeared, and it is a very natural question. Maybe you know at this audience the answer, but if you know, you should say me right now. And now it reminds me an anecdote because it is beyond uniform hyperbolicity. I participated in the first Beyond of Uniform Hyperbolicity as a PhD student with a lightning talk. And the lightning talk was 20 minutes. And it was, the lights were different. And the talk was at Evanston, first Beyond Uniform Hyperbolicity. I remember that my chairman was Charles Pugh, and I suppose that we didn't have Blackboard. We have just slides, and then we had some flip chart to use to write over the paper. So, you know, I was PhD student. I would like to talk about my stable ergodicity without partial hyperbolicity results. So I was writing and writing and writing, and time passing, and suddenly the paper finished, a flip chart. And my time, of course, it had finished before. And Charles looked at me, okay, your paper is finished. So I finished. What I think is that I began my history of beyond uniform hyperbolicity, beyond, in fact, with the dominated splitting, which is the less maybe hyperbolicity available. Well, it is projective hyperbolic, but and then I went through partial hyperbolicity, and I think that I'm trying to convert to the uniform hyperbolicity. So the uniform hyperbolicity seems to have many, many questions still to be addressed. So, okay, so let me now change to U equilibrium states. And another figure, another person which will appear, who fortunately is here. And this is a very nice argument that I like very much. I hope that I am not losing my time. And this is a convexity argument that we call it the Le-Drapier argument. So I know that many of you may know. Maybe you think that you know. But so this is a very nice history. It should be counted someplace at beyond. So U equilibrium states, the definition is similar to the UMME, measure of maximal entropy, and we know that they exist because this functional is again upper semi-continuous. You know that it is it attains because the unstable entropy is upper semi-continuous, as Jerome told to us. Okay, so you have always a measure of equilibrium state. Sorry? What is the setting? Yes, the setting for some continuous function, some partially hyperbolic diffeomorphism. Yes, in fact, you can consider any expanding foliation, anything that varies upper semi-continuous. So okay, I'm not good with this thing. Okay, so maybe before talking about a convexity argument, I would like about a technology that appears to study these equilibrium states, which is the notion of conformal measures. Or maybe for today's talk, or for this mini course, we'll call it Phi-Margulis family. So what is Phi-Margulis family? You consider a foliation. It is general. The definition is general, but let's us concentrate on some expanding foliation or even unstable foliation of the partial hyperbolic diffeomorphism. And you have radon measures which are supported on the leaves, and they have this conformal Jacobian. Okay, so after iteration by the dynamics, you have this conformal the radon derivative, radon-Nikodym derivative. Okay? Generally, as I said, we require that these measures are measures which are defined on the whole leaves. And they are constant on the whole leaves. So this is a measure on the leaf, depends on the leaf. So we require constant on U leaves. I mean that MUX is equal to MUY as soon as Y belongs to the same leaf of X. MUX is the family, and saying that it is constant on the leaf means that it is constant as measured. So again, this is an exercise to show that, similar to the thing that Jerome proved yesterday for the volume growth, even easier here, you can prove that if there exists a Margulis family for the constant potential, phi, and if as soon as you know that your measures are uniformly radon, I mean the size of the balls are uniformly bounded, then the same argument that Jerome used yesterday, you have a lower bound for the unstable entropy in terms of this constant. And this constant, remember that is the constant of conformality that appears as the conformal constant of the measure, the Margulis family. So the proof is similar to the thing that he did. So you consider a measure, a subset, a compact subset of positive measure. Then you consider, you have a positive measure subset, compact subset. You consider n epsilon a spanning set, and then you iterate. So you cover by balls the image of Fn of k, and it is less than the sum of the measures, and you know that your measure is conformal. So here you have p power n, the measure of k, and here you sum times the number. This is at most the number of a spanning set, a spanning n epsilon, a spanning set, times the measure of a ball of radius epsilon, okay, in the future leaf. And you are assuming that it is uniformly bounded, and then you take logarithm and divide by n and take n to infinity. It is the usual arguments. And now I would like to address the inverse. So the inverse, in fact, the inverse for the unstable foliation, the inverse also can be proved. Again, as Jérôme told us, the entropy is, okay, I caricature proof of that logarithm of p is less than the entropy, and you can also prove the entropy of f, u entropy of f, is always less than the logarithm of this constant, this conformal constant. I'm assuming that phi is 0. This is the case of phi equal to 0. So remember that here, definition of Margulis family is that f star of mu of x is equal to exponential of minus p mu of fx. Okay? So the other side, this side, that the entropy is bounded above by the logarithm of p, as soon as you know that the foliation is expanding, you can use the argument of an epsilon separated set as appeared yesterday, and you can prove, but you can prove much more without using expanding foliation and the abstract notion of existence of subordinated partitions as appeared in the Jérôme's talk also. So this is why I will put one of the reasons that I put here, but this argument is everywhere. So L-Drapier argument is that if you consider a diffeomorphism which is C1 on a manifold, and you consider a potential which is continuous, and suppose that you have an expanding foliation. In fact, this is not necessary to be expanding foliation. You will see as soon as you assume the existence of some ordinated partition to this foliation, everything will be with respect to the entropy of this partition. So let me, for the sake of easiness, assume that. So these are hypotheses. Suppose that you have family of measures such that they are phi Margulis. So mu of fx has this conformal property, okay? And maybe this is one of the most important things also. Not most important, one of the very important thing is that the measures are supported on the whole unstable leaf. So let me just put it here. So you have the Pierre argument. So I have Margulis family of measures. They are conformal. It means that mu of fx is equal to exponential of pi minus phi mu f star of mu x. And I know that a support of mu x is the whole leaf. Okay? Then what you conclude is that for any invariant measure, the unstable entropy of your measure plus the integral of the function is less than p. Okay? So okay, as I like this thing, and I have a good blackboard, I want to write the proof, but as I don't have very good memory, I need to cheat. So as I said, just subordinated partition is necessary. And okay, there is another personality which appears, who is Johann Jensen. And Jensen was, yeah, you wrote it. Well, you can see the history. Maybe he was Danish, and he went to Sweden with his family, and supposedly he never had any mathematical academic career, but he was just self-taught, and he had very small number of papers, but many papers are useful, of course. I think he had also some contribution on Riemann zeta function. In fact, it was nice. Yesterday night I was just verifying this paper. It is some 6 or 7 page paper to ACTA, and the paper begins with a letter to Mittag Leffler. He wrote, "Dear professor, I have a very important result." In fact, the title of the paper is an important result in complex functions. So, and then, okay, the result is about the average of logarithm of norm of holomorphic functions. It related to the zeros of the function in the disk, some subharmonic function. The average of the function is related to the zeros. And this relation appears so many logarithms, it reminds me, this is again Le Drapier and Young, something like, there are log and some sum of them. Okay, so the slogan is that log is concave function. Okay, I have always difficulty to define concave and convex. So concave means that like this part of the mustache, concave, and convex is over there. So the result, the Jensen inequality says that if you take the logarithm of the integral of a positive function, then it is, okay, if it is probability measure, if you have a probability measure, then the logarithm of integral of phi d mu, so this is always larger than integral of logarithm of phi d mu as soon as phi is positive, okay, and phi is a positive function integrable. So continuous integrable. So if, when it is not probability, you should normalize and you should add something here, okay? So you divide by the mass of the whole space and you just adapt it. So let me just write also this one that I will use. So logarithm of the integral of a function over m. Let me write it more decently. Logarithm of the integral of a function is always larger than logarithm of the mu of m plus 1 over mu of m integral of logarithm of phi d mu m. Okay, so now let's just in some two or three slides show you how the argument works. So suppose that p is 0. Just for the sake of simplicity, you can just remove the p from your potential. You can assume that p is here equal to 0, and we have the Margulis family of measures. You want to prove this inequality. So first of all, you define normalized Margulis family, or probability Margulis. So by this, you just normalize the measure of mu on any psi of x. Okay, so psi is a subordinated partition. Okay, so you have a subordinated partition with respect to unstable. So psi is subordinated to fu. Okay, so by the very definition, almost surely they contains open sets, and as soon as you know that the support of these measures is the whole leaf, so you know that you can normalize, so the denominator here is not 0, almost surely. So you have a notion of probability measure on the atoms of the partition. So here you have psi of x, so this is psi of x, and here is f of x. So this is psi of f of x. So you have, by Rochlin decomposition, you have probability measures and for every measure. But here you have the Margulis measure, which is not a probability measure. It is on the whole leaf. You just normalize it, and you have this probability measure, which is normalized Margulis measure. Okay? So now you have one very important step that appears in ergodic theory courses, should appear at least, is the Gibbs inequality. The Gibbs inequality says you that the entropy the unstable entropy of the measure, which is by definition, as appeared yesterday, the logarithm of mu psi x of f minus psi of x d mu. You average, okay, you consider, you average the conditional information, and the Gibbs inequality says you that if you take the average with respect to a wrong probability, then you always get something larger. So if you take with respect to Margulis normalized family of measures, the mu, then the average that you have is larger or equal than that one, okay? So this is again the convexity argument. So good. So how do you show it? You just sometimes it works, sometimes it doesn't work, or I don't work. Okay. So what is the quotient? So here you take this to other side. You are taking the average of the Margulis measure of the f minus 1 of psi divided by the conditional measure of mu. So here you have psi of x, and you take f minus 1 psi is a partition which is finer here. Okay, I have an increasing subordinated partition. Okay, this is the right condition. And then this integral, you can use the definition of conditional measures. So you can decompose the measure along the atoms of the partition. So you take the disintegration, and when you take the disintegration, this inside integral, okay, this inside integral, you use Jensen inequality. So you take log outside, and here you have integral of m mass divided by mu mass. So m is the normalized Margulis family, as mu is the conditional measure of your invariant measure. So, so this is, you can see that, okay, this is a sum, a countable sum. As soon as you know that the entropy of the entropy of partition is finite, so if you refine by f minus 1, you have countably many non-vanishing atoms, and you just open this integral. Whenever you open this integral, all of them will be, just by the very definition, are equal to 1, and it is log of 1 equal to 0. Okay? So, and observe that equality holds whenever mu psi and mx, these two guys are equal. So we have equality in the Gibbs inequality if and only if mu psi x of f minus 1 psi of x is equal to mx of f minus psi of x. So if you want, mu psi and mu psi x and mx agree on the f minus psi sigma algebra. Okay? So who knows letter Young, this appears there, these arguments. So now I want to finish the proof of why the entropy, so why the entropy plus the average of the function is less than 0. So the entropy is written, well, this is not exactly entropy. This is, in fact, larger than entropy, okay? And we have to, I will have two expressions. One of them is minus logarithm of Margulis on the refinement of initial partition. Another one resembles the integral of the function. So here you have some other measure here is appearing, which is just a probability measure on the f minus 1 of psi of x. Okay? So here, the second thing, let me just comment that the first thing by Gibbs inequality is larger than the entropy. So the entropy is less than 1. And this guy is less than minus integral of phi plus epsilon. As soon as the diameter of the f minus 1 of psi is small enough, if you take any small enough partition, so observe this expression. This expression is almost the integral of the function with respect to the measure mu, except for here you have not the correct disintegration. You are taking some other measure, some other probability measure. As soon as the atoms of partition are very small and phi is uniformly continuous function, then you conclude that your approximation is good. So this is less than minus integral of phi plus epsilon. And okay, and then you send epsilon to 0. This means that the entropy of the measure is less than minus integral of phi. Okay? So I should define for you what are these measures, and more importantly, why is less than 2. 1 is less than 2. So, sorry? Sorry? Phi is the potential. Yes, yes. I'm sorry, I sometimes, okay, my LaTeX font is this phi. Yes, yeah, okay, thanks. Okay, so, okay, you lost my joke. So we want to prove that 1 is less than 2. And the 1 is the entropy. 1 is less than the entropy of the 1 is exactly larger than the entropy of the function, and 2 is less than the integral of minus integral of the function. So be patient. So the first one we proved. It was Gibbs inequality. And the second one is just the let me say, wait, I should come back again. Yeah. Okay, so let me use my notes. So I want to prove 2 is less than, so I want to prove that integral of minus logarithm of normalized measure of Margulis measures, if I take the average of these things, it is all, I want to prove that 1 is less than 2, which is equal to something that I will write at the end. Okay, so let me just develop this. This is the integral of minus logarithm of mu. So you remember that mx was the normalized Margulis family. So the normalized family was when you divide by the mass, the mu, okay? So this is minus log of mux f minus 1 psi of x d mu plus integral of log mux psi of x d mu x. And here you should use the conformality condition, which says you that this is equal to minus logarithm of. So what is the measure of? So what is the measure of this small part? The measure of this small part is the integral of indicator function on this small part, but you use that the conformality of these measures. So it is equal to f minus 1 psi of x exponential of phi, this is the Jacobian, d f minus 1 star of mu fx. So you go to the next leaf and you pull back the measure. This is exactly the conformal condition, and this is I am taking with respect to measure mu. So this one I will continue carrying plus the same thing. And here, I need to use the convexity argument. So here, this measure is not a probability measure necessarily. So if you take mu of fx, f minus 1 star, this is not a probability measure. So I need to normalize it and use that normalized Jensen inequality. So I use it, so you can verify later. It is f minus 1 psi of x. So logarithm goes inside minus phi z. So this d nu is the probability measure. I normalize this measure, and then I should pay the cost, which is negative, of logarithm of mu fx of psi fx, which is exactly the mass of this guy with respect to this measure. So the mass of this guy with respect to this measure is exactly mu fx of psi fx d mu. So you see that I have three terms. One thing, okay, here I have, I am losing something, maybe d mu also. I have d mu. Okay, this is the d mu. I still have it. So I have three terms. One term is I have first term. So eventually, oops, that's not usual. The entropy is less than, we conclude, or one is less than entropy of m f minus 1 psi x of my potential d with respect to some probability measure on the atom of f minus 1 of psi d mu plus two terms, in fact, minus log mu fx psi fx. So you see what is appearing here, mux psi x d mu. So this is almost there, and this one, if you are beginning your ergodic theory course, you will cancel it with that. But then you will think a bit more and say, oh, why I can cancel it? Can I cancel it or not? And this will be an exercise. It is a classical exercise that you can cancel out here. Integrability issues are not important here. So one will be less than this thing, which is 2 plus epsilon 2, in fact. So this in fact is less than integral of minus phi plus epsilon, as I said, as soon as the psi partition is fine enough. Phi is always the same phi, Lawrence. Well, I just apologize to you that this is not, yeah. Yeah, at least to be coherent here. Okay, yes. No, yeah. Everything is this phi. Okay. No, good to have a pause. Okay, so now I am happy because I exposed it on the blackboard of ICTP, this argument of these guys, people. And now, as I said, you concluded that the measure, conditional measure, is equal to the Margulis measure on the sigma algebra of f minus 1 of psi. And then this thing is the test of vision. You don't need to read it, of course. This is to say that after an exercise in probability theory, you can iterate the argument and prove that, in fact, these two measures coincide on the all f minus n of psi, all of the pre-image of the partition. So we prove this. The first iteration, you can induce, make some induction, and prove that really you can do it. And as soon as you know that this partition is generating, it means that you have the full equality of these two measures. So what we concluded is that as soon as you have some continuous function, some Margulis family with this condition of full support, then we prove that the entropy or the pressure of any measure is less than 0 here. So we have this part of. So the problem is the inverse. So what can we say if whenever the entropy plus integral is p, so here p is appearing. I just used p equal to 0 just to easiness. So I just removed from the integral of the function. So in general, you have entropy plus integral of phi equal to p. What we can say about the measure mu, okay, So this is an exercise again. Try to look at the argument that we did here and see why it is not true to conclude that equality implies that conditional measures are equal. So one fake proof is that just looking at this argument that I put for you and say that, okay, as soon as you have the equality, then I should have equality in the Gibbs inequality, and then I have all the history, and the conditional measure of mu should be equal to the Margulis measure, but it is very, very elementary fake proof, and it is not true because we are using 2 times convexity argument, okay? So what is true is that now for any Holder potential function, no phi will be Holder, so you assume that phi is Holder regularity, and you have an equilibrium state, equilibrium measure for this phi, okay? So it means that entropy plus integral is equal to the pressure. Then what you can prove, again, is that the unstable conditional measures of your measure are equivalent to the Margulis measures, which were the conformal measure that you began. Okay, this appears in, again, Le Drapier-Young, and it appears for this general potential and with good amount of details in a paper of Pablo Carrasco and Federico Rodriguez. And what is the density? The density of this measure with respect to the conformal measure is explicitly written here, okay? This is a nice trick also, which who knows Le Drapier-Young knows that this trick, okay, these tricks appeared several years ago, but that's very nice because it has many conditions, many consequences, as you know. It is not just absolutely continuous, it is equivalent, and you know that the density is a very good function. So this is for any Holder potential. This is written in Pablo and Federico's paper. So whenever you have an equilibrium state, you have the reverse, which is just absolute continuity and not equality. If the potential is 0, of course, this will be the same measure. So I will have, okay, maybe negative. No, I have a good amount of time. I will give you some informal roadmap to U equilibrium state because these things help us in the literature to construct U equilibrium states. So how typically we construct U equilibrium states, which can be useful to construct equilibrium states themselves, okay? So you begin to construct some conformal family. So you have a potential phi and try to construct a family of conformal measures on the leaves. And suppose that at this moment, phi has U-Bowen property. Okay, so if you are in the expanding foliation, Holder is enough, Holder continuity, but in general, assume the U-Bowen property, and then it is kind of again classical to prove that whenever you have this conformal family with this condition, then you can calculate, you can estimate the measure of Bowen balls on the unstable leaves. So the measure of Bowen balls will be something like this exponential minus NP plus the Birkhoff sum, but still it is tricky because you are talking with measures, MUs, which are defined on the manifold, on the leaves, and these measures typically may not have any continuity property. So this is something very subtle and important, is that if you want to prove this Gibbs property, which will be almost to prove U equilibrium states, from here you will have kind of Green-Katok result to prove that you have equilibrium states. But to arrive this for some uniform constants, Q's, okay? So some abstractions, is that MUX, this family of measures that we defined, are not necessarily continuous, are not varying necessarily continuously. Although it is not the most necessary condition. You can relax it, or maybe something like this. You can have mu of x, so you have mu of x. As soon as you know that these measures have some Jacobian, so here is x and here is y, this is fu of x and here is fu of y, and you see that I have a measure on here, an unstable leaf here, and a measure unstable leaf here, and then I have transverse foliation, which is the center stable. As soon as I know that I have a good Jacobian between these measures, then, okay, everything will work, and you will have Gibbs measure. And again, this appears in 2 papers with 2 different approaches. One of them is the construction by Klimenhaga, Jakov, Pessin, and Agnieszka Zelerovich, when they use Karateodori construction to construct this Margulis family of measures. These measures are kind of Hausdorff measures, similar to construction of some Hausdorff measure. And Federico and Pablo pushed the Margulis argument and also constructed this measure under some hypothesis when the center, well, here also you have hypothesis on the center bundle. So I'm just here reminding the way that Klimenhaga and Zelerovich and Pessin used the Sinai type argument. You begin with your Margulis measure. You take your Margulis measure on some unstable leaves and you iterate it. You know that it is conformal, and then you take any limit measure. The conditional measures are equivalent to the Margulis family, and then you can use it to prove that under these conditions of center, they have some condition on the center bundle. As I said, here you need something on the transverse direction. The condition is that you are like isometry, okay? I will not enter into the details. Probably tomorrow when I talk about discretized laws of flow, which share something similar to these things, I can talk about that. I think that, okay, I will not construct these measures. Yeah, maybe I should just finish to say that these measures were constructed by many of people in several, maybe I am failing to announce some of them, but okay, the thing that I have read in this, to prepare this mini course, this construction by Klimenhaga, Pessin, and Zelerovich. There is a relatively older work by Boris. They construct geometrically these measures, Hammerstadt, Haydn, and the Pladeur for flows, Anosov flows, Ruel and Sullivan for invariant sets, hyperbolic invariant set, and using a transfer operator theory in some non-uniformly hyperbolic setting by Steer. Okay, so thank you very much for today so far.
Questions for Ali? Yeah.
So just one comment about your question. Like with Jagan, we can show like for 3-dimensional of center expanding, like UMME equals to MME if and only if like your center are rigidity. Like you have SU integrability or center everywhere, like exponents the same with the linear. That's the
Sorry,
effect.
you mean this non-integrability quantifier?
No. Just like if your UMME equal to MME.
If it is equal.
If it is equal, if and only if like your center exponents are rigid, like all equal to the linear one. Okay, so
center exponents with respect to
with respect to yes,
MME.
no, every point.
Oh, every point.
Yeah, every point. So that's UMME equal to MME. Every point exponents is linear.
Is zero.
It's linear.
Linear.
Yeah,
It's like linear.
Yeah,
Really,
it equals
really.
to linear. So yeah, that's also like.
That's very good.
Oh, yeah.
Thank you. Okay. You send me.
All right, if there are no other questions, let's thank Ellie again.